Yeah, okay, please, Basti.
Okay, so thank you, Jeff, for the opportunity. I will talk about this normalized generalized Ritchie flow on thaloric Fano varieties. We just uploaded a preprint, the three of us, Jeff Streets, Yuri Ostinovsky, and myself. So try to cover some part of this in, let's say, two talks. We'll see how this goes. So here is the general plan. I will start by recalling some facts about Ritchie flow. We already spent some time about this, but I just want to fix some notation and to recollect some of the facts. Then I will briefly reintroduce the generalized Ritchie flow and its normalized version. Today, the plan is to at least tell you what are the main results and to briefly discuss some of them. And probably for the next lecture, I will specialize in the toric case. It's to tell you how in the toric case the generalized scalar geometry can be simplified, and because of this simplification, we can reduce essentially the flow to something very familiar in Kähler geometry, and therefore use some of the techniques available to prove some of the results. So let's go. Yeah, and be free to just cut me and ask questions. I will be happy to indulge in some discussion along the way. Okay, so Kähler-Ritchie flow. We consider here a fixed complex manifold, which is 2n dimensional air manifold with an integrable almost complex structure. And we will pick an initial Kähler metric. So we have a Riemannian metric, which is compatible with a complex structure, and its fundamental two form is closed and symplectic. That's a Kähler structure. And so we consider this a normalized Ritchie flow, which is just the flow of Riemannian metrics given by prescribing the time derivative of the metric being minus twice the Ritchie tensor. Ritchie tensor is a symmetric to zero tensor, precisely the same type the Riemannian metrics are. And we prescribe the initial condition in this Kähler initial metric. So that's the. In this setting, the first observation is that it's well known and well established that if we start from a Kähler piece, this flow will remain Kähler. So all along where the solution exists of this star, the resulting metrics will be Hermitian and Kähler as well. And this is not a rigorous proof, but actually we'll see in a moment more rigorous proofs of this. But at least on heuristic level, what you can see is that if you gauge with a complex structure, the first equation star, what you will get here, so J is fixed. So since J is fixed, you will get a flow of 1/1/4 omega t. Omega t will be the Kähler form of GT. And these 1/1/4 will evolve by minus twice the so-called Ritchie form. The Ritchie form is the Ritchie tensor gauged by J. So this rho represents the first-order class, and it will be a closed object. So at least formally, you see that this will evolve by something which is close to the right-hand side, and we expect, of course, the solution to be closed. And indeed, that happened to be true. So the Riemannian Ritchie flow, if you start from a Kähler background, will remain Kähler as far as it exists. So the first remark, I think Jeff already made this, but the first remark we can see here is because the flow remains Kähler all the time when it exists, it will also introduce a cohomological flow, a flow of a finite dimensional object. So we consider the Durand classes of the Kähler forms, which evolved according to this Ritchie flow. And what is important is that so I probably just return. So what is important is that this right-hand side here is always just 2pc1x. So it doesn't change. Because of that, we have that along the flow, these cohomological Durand classes will have a fixed time derivative, and therefore we can solve this problem. We can say that alpha t, the round class of omega t will be alpha 0 minus 4p t c1x. It's just on logical level, you have this, this evolving the round classes. So one consequence of this remark is that in general, you cannot expect this flow to exist for all time. It's just because of this cohomological evolution. For instance, if you have a curve on which C1 is positive, then on this curve, I just restrict on the curve. We said that the flow generates scalar metrics. So when you integrate over this curve on the left-hand side, you have to have something positive. This is positive fixed, but then when you evaluate here, you have something negative, and when t is big enough, you cannot have a calorimetric solution. So this shows that in general, this Ritchie flow is bound to exist only for some amount of time. And the general conjecture, which is actually a theorem in the Keller case, due to many people, Tsao, Tian, Song in particular, the solution of the Keller-Ritchie flow would exist for amount of time until capital T0, where T0 is the supremum, the maximum T for which alpha 0 minus 4p TC1 is positive definite. Okay, so for t equal to 0, this is always the case because we started from a Keller metric. And for small t, this will stay so because it's an open condition. But also this inequality gives you a precise bound, and this is precisely the bound to which the flow will exist. So we have these cohomological abstractions for long-time existence. It's the first remark I want to make. Is it that clear? Any questions? So there are some cases, though, where we can make the flow to exist for all time, and that's probably what I'm going to discuss now. So the first such case is the Calabi-Yau case, and Jeff did a very good work to review this. I just recall what's going on. Just to simplify a little bit the discussion, I will assume that we are in the case when the canonical bundle of the underlying complex manifold is trivial. So the Calabi-Yau is simply connected. So in this case, if it's trivial, we can choose a non-vanishing section of the canonical bundle, which is just a holomorphic volume form on the manifold. It will fix this object. And little linear algebra shows that if I wedge theta by its conjugate, this would give me a 2m real, well, almost real. I probably miss some minus, so probably I to the n probably is missing in this expression. But up to this, this expression will give the norm of this theta with respect to the Keller metric. And because of that, we now can write the Ritchie form of a Keller metric in general. The Ritchie form is the curvature form of the induced connection on the anti-canonical bundle. So in this case, we have a section on canonical bundle, and we know the norm, and we know that actually this will be 1 over 2 DDC log this norm. So I incorporated the signs minus the fact that the Ritchie form represents the anti-canonical bundle, canonical bundle. So in general, you have to put minus 1 over 2 here. So in this situation, the Ritchie form has this very pleasant expression where we only need to know this theta conjugate to omega. So I can rewrite this in this identity as saying that the Ritchie form is minus 1 over 2 DDC log the Keller form to the power m divided by this fixed universal volume form. Okay, so just using this global section, I have this nice expression. And the other observation is that okay, so probably the other observation comes from the fact that remember here that I have alpha t, general alpha t, was equal to alpha 0 minus t for p c1. But in this case, c1 is 0, so this term is equal to 0. So so you see immediately that this cohomological abstraction is trivial. You stay in the same class, and this class already carried. And I will take advantage now of this as well in another way. I can write now. The solution. So omega t is the solution at time t. So it's a Keller form in the same Keller class omega 0. So it's the same Keller class as omega 0, the initial metric was. So in particular, this omega t, omega 0 are cohomologous, the rank cohomologous, and you have this Dirichlet lemma in Keller manifold, which means that you can actually write the difference as a derivative of a function. So this function is defined usually up to a constant, but let's ignore this for a moment. So I could write this omega t as omega 0 plus dDc phi t. If I do that, then what happens is that I can now look again at the definition of this Keller-Ritchie flow. So we have ddt omega 0 dDc phi t is equal to, because of this minus 2 times the Ritchie I took, I will have dDc log omega 0 plus dDc phi t to the m theta plus theta. And now omega 0 is time independent, so I can pass ddt to the phi t factor, and I have dDc of derivative of t is equal to dDc of something else. On a compact manifold, this means that the scalar terms has to differ by some constant. So the upshot is that we have this. Along the solution, I could write this identity. Now, if you look at this identity, what this represents, it represents actually a parabolic scalar PD. So it's a PD for a time-dependent function, and you have pretty well established theory about local existence. For instance, you can immediately say that this is a parabolic PD. So it will admit solutions for small positive time, and this is also proves you that actually the flow we started with is really a Keller flow, because the solution of this will generate a solution of the initial Ritchie flow, and we saw in Jeff's lectures that it will have some sort of uniqueness of the solution. So here's the point. So the important observation is that in this Calabi-Yau case, we use the cohomological assumption and the Dirichlet lemma to rewrite the initial flow of tensors to flow of functions to a PDE. Okay, so that's sometimes it's called scalar reduction. And using this as kind of a starting point, Tsao in 85 proved this beautiful result, which gives alternative proof of the Yau theorem, which says that this nonlinear parabolic PDE, if we normalize it in a certain way, will admit a global solution, which will define for all values of t, so positive values of t, and moreover, it will converge to something. Actually, it will converge to a metric which has this property, and this is a Calabi-Yau metric, because the volume form of this metric will be equal to the volume form of theta that we started with. This characterizes by what we said before, and the fact that the Ritchie test is 0. So, and Jeff did a very thorough presentation of proof of this result. Okay, so the important point here is that we had this for all time we had this nice cohomological trivial assumption, and we use it with Dirichlet lemma to reduce to a scalar equation, and then with scalar PD there are techniques using, I'll probably talk about the techniques, PD techniques later in the talk. So perhaps, yeah, so there is another case that this can be done, and this case will be of particular relevance to us because we are interested in generalized scalar geometry. Well, Tsaw's paper actually has 3 cases in which he can prove existence. Keller-Einstein metric, there is this negative Keller-Einstein case, but in the negative Keller-Einstein case, there are no holomorphic Poisson tensors, so it's not something which is natural in the generalized scalar geometry. So I will focus on the positive case, which is the Fano case. So what happens in the Fano case? The Fano case is when the first Chern class of the underlying manifold is positive definite, and by Yau theorem it can be represented by a Keller metric with positive Ritchie curvature. So in this case, we will pick an initial Keller metric which is already in this positive Chern class in C1. Okay, so we will make this normalization assumption that we take exactly the 2p C1 X as cohomological class, and with this assumption, we will, instead of the Ritchie flow, we will introduce a modified version of it. Instead of minus twice Ritchie, I will add this twice G tilde T. So it's like the Ritchie flow, but with this normalization factor. And this is from the point of view of local theory, this is very innocent modification, because you could actually link the solution of the original Ritchie flow to this modified or normalized Ritchie flow by some sort of obvious substitution. I think the precise formula is this. So if GS was a solution of the Ritchie flow, and if you reparameterize it like this, you get a solution of this 2 star, and vice versa. This also can be reversed in that way. So all the local properties of the flow stay the same because of this obvious fact. In particular, this will, if we start from a Keller metric, as we want to do, this normalized Ritchie flow will remain the flow of Keller metrics in particular. Okay. So the next thing we will do is, as we did before, is to consider we will gauge with the complex structure and consider the flow as a flow on Keller forms, on 1-1 forms. So the corresponding flow to this will be a flow for 1-1 forms, which will be of this form, and we know already, because of the local properties, that this will be a flow of Keller metrics. And now, what we will do the same trick. We will now consider the Durand classes in this relation, and we will see what will happen with the homological abstraction for long time existence. So in this case, we will have the ODE that the derivative of alpha t is minus 4pc1x, which is a constant, plus twice alpha t. You can solve this ODE explicitly. And now I will use the initial condition is that alpha 0 is 2pc1x because of what I assumed upstairs. And if you play a little bit with this thing, we will find that actually alpha t will remain equal to alpha 0 along t. So in particular, again, the homological abstraction for long time existence is satisfied with the normalizations we have chosen. And we will play the same trick. So because of this, we can write the solution whenever it exists as omega 0 plus TDC phi t. And we can also, express the Ritchie form in a convenient way. The most convenient way probably is to introduce the Ritchie form of the starting metric. And then you can rewrite the flow in this specific way. So the time derivative of et is logarithm of this volume form of omega t, written in the potential way, and divided by the volume form of omega m, omega 0m, the initial volume form, plus twice phi t, which comes from here. And I don't have a global, I may not have a global section of the canonical bundle to play as before, but I think a local section and re-express this well-defined quantity as a difference of two Ricci forms, the Ricci form of omega t and the Ricci form of the initial metric. To recompensate, I have this factor h0, which is just what's called Ricci potential. It's a smooth function such that the initial Ricci form minus the initial Keller metric is the DC of this h0. So this object exists just because these are two forms in the same cohomology class. By Hodge theory, it exists. You have to take a trace here and solve a Laplace equation to find such h0. We find it once for all, and then you can rewrite the whole flow as a scalar PD. So are there any questions at this point? So we played the same old trick to start with a Riemannian flow, then observe its scalar, and then play with the cohomological components to reduce it to a scalar. Now, this just very fact that we have been able to reduce to a scalar been used actually by Tsao, who in this Safaro case was able to establish that flow exists for all time. So he proved the all time existence of this parabolic PD for one scalar function. Okay, so this result is not obvious. We saw in Jeff's talk that it requires a lot of work, but roughly speaking, the idea is the following. We can just renormalize. So probably this normalization constant, you should think of this normalization constant coming from, so instead of phi t, we can consider always phi t plus just a function of t. If I substitute, I will still have the same flow of induced scalar metrics. And if we do that, the terms in the log doesn't change because they define the differential of phi t. So the only thing will change, the only change it will come from here and from here. So this CT, if you want, is a constant which allows us to renormalize the phi t solution. So it's kind of a normalization constant. So from that perspective, what so we can do, we can assume without loss of generality that actually the CT is 0 up to appropriate normalization of phi t at each time. And if you do that, we can consider the flow without any constant. And if you take one derivative to the initial flow, you will end up with some. So I linearize essentially. You will end up with the following linear PD. So the derivative of phi point will be the Laplacian of phi point plus twice phi point. Okay, so what happens? So from here, if you have such a thing, what happens is that you can play with the maximum principle. So if you consider the quantity which is exponential, so if you consider exponential minus twice t phi point, so this guy will so this is psi. it will, this guy will satisfy a heat equation. And because of that, so we have this maximum principle. So what happens that you can derive for a fixed time. So you can derive a C0 bound for this psi. So because of that, turning back to phi dot, we will have a C0 bound, which will be exponential 2t universal cover. So it will. So we don't have a C0 global bound, but finite time. If the time is between 0 and T0 in capital T0, say, this will give you a C0 bound on phi dot. And from this C0 bound on phi dot, you have also a similar C0 bound for phi t, just using that. Mean value estimate. So this very simple manipulation shows you that you could, for finite time, if you want just to see what happens up to some fixed finite time, phi dot and phi will be both C0 bounded. And if I return to this equation without the factor C here, so this guy will be C0 bounded. So this will be C0 bounded. This will be taken care of. This will be taken care of by this C0 bound. So this is a priori given H0, so it will be bounded. So you get C0 bound of this term. And then you use the Yao estimates. So Tsao used the whole Yao machinery to say that if this Morge-Ampere operator, you have a C0 bound, then you could derive further higher order estimates, and eventually you could always prolong your solution beyond this finite time you have chosen, because at some point by Arcelor-Ascoli you could define the solution of this fixed time, and then you can be beyond by the local existence. So the usual argument you see in ODE for global solutions. So this was the kind of a big event in 85. This result of Tsao, which in particular show global existence of the normalized Ritchie float on a final manifold. But then nothing happened until relatively recently. Because this final case is notoriously difficult for proving global results. Of course, there were a lot of intermediate progress, but probably the kind of a final touch of this story is a result by Tian and Su from 2013. So what they prove is that if you have a final manifold, and if you assume that this final manifold admits Generalized time metrics, that's not always the case. There are many finals which don't admit Generalized time metrics, and that's where all the troubles come. But suppose that we are in the ideal situation. You know from the beginning that you have a Generalized time metric. So then what they proved is that actually this global solution given by the Tsao theorem will converge when t goes to infinity to another possibly different Generalized time metric. The problem is that you may have automorphisms, and these automorphisms will act on Generalized time metrics, so you have a whole orbit of them. So the idea is that if you start with this scalar Ritchie flow and you normalize it in a convenient way, so then this CT will definitely be non-zero for the theorem to hold. Then these potentials will converge to some smooth function in a polynomial rate, by the way, and this smooth function phi infinity will correspond to some Generalized time metric. And perhaps just to emphasize again, the role of normalization of constant is important. Actually, the key new event which allowed this result to be established is so-called Paramount's estimate. So what Paramount's estimate means is that so Paramount show that you can normalize the constant Ct in such a way that phi dot t will be time independent, uniformly bounded. So if we go back here, this guy will be C0 bounded. Of course, this will be okay. Well, the normalization constant doesn't matter much, but you still have a problem actually, because you don't know that phi is bounded. So the main issue was to, even with Paramount's estimate, to prove C0 estimate to phi t. So that was the big missing bit, and that's what Tian and Zhu achieved in many steps. I think their first work was short after Paramount, probably 2003. They had a kind of a weaker convergence result, and it took some work to get the controlled convergence result in potentials, as I stated, and it does use the C0 estimate, which is fairly non-trivial, plus Paramount. Anyway, so this is kind of a quick overview of the Keller-Ritchie flow. So in summary, what's important for us to observe that we have this reduction of the initial flow to a PDE, and this PDE is defined on a functional space. Functional space in question is the so-called space of Keller potential. So we fix an initial Keller metric. We consider the smooth functions on our manifold, for which omega 0 plus DDC of the function is positive definite. So this is kind of a fresh open subspace, space of C infinity functions. Modulo constant, by the way. Constant doesn't matter in this. This resulted actually by Didibal lemma from the notion of a Keller class. So the notion of a Keller class is just a de Rham class of which contains Keller forms, and if you have two Keller forms in the same de Rham class, it's necessarily given by such Keller potential. So these were the two main underlying ingredients that allow the reduction of the flow to a scalar PDE. So in particular, in these two cases that I consider more thoroughly, we had this worked pretty well, and we had a nice reduction indeed to such scalar thing. So now we turn to our main subject of interest, is this generalized Keller-Ritchie flow.
Can I ask a question?
Yes, sure.
Yeah, so I just wanted to ask if you could explain a little bit more about the fact that the limit of this procedure could be a possibly different Kähler-Einstein. I'm just wondering how I should think about this result. I don't know if you have any.
Yes, right. So even on CPN, you have the A Fubini-Studi metric, and then you have a huge group of automorphisms, and it gives you a whole orbit of Fubini-Studi metrics. Now, the problem is that reducing to a scalar equation, we killed completely the possible action of automorphisms, because the automorphisms, they will move the metric. So the Keller-Ritchie flow fixes, it's kind of a transversal to this action. It fixes the Keller metric along the flow, and it fixes the Keller potential. And you cannot expect that you will pick a given metric that you started with just because this flow is uniquely determined. So you have a unique solution. So it will go, the trajectory goes somewhere. So what the theorem says is that it will hit the orbits of Keller-Einstein metrics. All Keller-Einstein metrics are isometric to each other. Okay, so there is this uniqueness result of Bando-Mabuchi, which says that any two generalized time metrics are isometric under the action of an element of complex automorphism group. So they're geometrically the same, but you have a whole orbit, and then this flow has to hit somewhere, but you don't know a priori where. Okay, is that answers a bit?
Yeah.
So yeah, it's right. So
it's
uniquely,
in other words, it's not surprising that this phenomenon occurs.
Absolutely not. Yeah, that's normal to deal with. And by the way, this
but let's
causes
say,
a lot of trouble. Yeah.
Suppose that you wanted to change. I mean, you could, of course, apply automorphisms at the beginning to your initial data, and the thing would be equivariant with respect to this. But I guess the point is that you don't know, somehow, you don't know exactly what the correspondence is, like between initial data.
That's the problem. So by the way, there are some, so the initial results, for instance, the result from 2003 of Tian Shu stated the same thing. But they say that if you have the Ritchie flow, then you could act each time you act with some automorphism, let's say sigma t, and you will create something which will converge. This was the first result that they proved, but they could not control. You know, this what you gauge with is implicit. You don't know what it is. There are similar results about Keller-Ritchie solitons. For instance, Keller-Ritchie soliton is a notion a little bit more general than Keller-Einstein. It's more frequent as well. Then for what I know, I think the best result is still convergence up to actions of automorphisms. Is this Shiger-Gromov type of convergence? So you could not control precisely with which automorphism you have to gauge to get a convergence. So it's a subtle point, actually, the automorphisms, because of what you say. And remember that the complex automorphism is a non-compact group, so it could create really.
Can you repeat that last thing? The complex automorphisms are what? It's
a not compact group, so you could not, you know, they could really go away from in any sensible tensorial norm.
Okay, yeah, thank you.
So
yeah. Can you say something more about how this Paramount functional allows you to control this constant? I didn't.
Oh, right. It's the Paramount normalization, you mean?
Yeah.
I think I have it here. Right. Yeah. So the normalization is following. So you want so this HT. Okay. So probably I need to clean up a bit the mess. So okay. So here we go. So I will denote HT. So this bit here will be HT without CT. Sorry. So okay. Oh no, with CT. Sorry. This will be HT with CT. So the condition is that I want to choose the constant CT such that when I integrate this whole quantity, HT, so exponential minus twice HT, with respect to the corresponding metric omega t, must be equal. The volume must be constant, must be equal to 1. That's what Paramount proposed. So it's not immediately clear that you could renormalize like this because of so what you have to prove is that you can add a function on t to the phi t such that the resulting thing satisfies this equation, but it's an easy exercise. You could solve this ODE to see that it's always possible. So that's the gauge which gives you the uniform C0 estimate of phi dot, and so
also maybe I just add one thing, like the reason for choosing this. I mean, the reason for this perhaps funny looking choice, e to the minus 2 HT integrated against the volume form is 1, is precisely so that then H becomes like a valid test function for the for his entropy functional. So you have this sort of unconditional entropy monotonicity, which is sort of, it's kind of like a Sobolev kind of quantity for, so it's like a certain kind of like log Sobolev quantity, which requires you to input a function which has like a volume normalization condition like this. Mm-hmm. And so, yeah, so basically the idea is to use the Ricci potential H as a test function in the entropy functional, which is, yeah, so as I say, it's kind of this like log Sobolev inequality, but also it has a scalar curvature term. And there's this kind of very delicate cancellation that occurs using the relationship of H to the scalar curvature. And that gives you a kind of like supercritical estimate for H, which then lets you sort of apply some iteration arguments to get the C0 bound.
Jeff, could I ask just about what you just said? So does this HT, you know, the way that it occurs inside this condition, e to the minus 2 HT integral, right? Is it used in this same way to define function spaces? Is it part of the measure or something? Or
well, yeah, that's sort of the point. Yeah, like in a sense, you're I mean, one way to think about these Paramount monotonicity formulas is that you're sort of fixing a background measure kind of, and then you get some monotone quantity sort of relative to that measure. That's one way to think about what he's doing. Yeah.
Actually, there is also a geometric reason why this is natural. If you, I don't know if I went through this, but there are these functionals at Keller-Einstein's metrics are critical points of it. There are two of them which compete. This is the Dink and Mabuchi functional. That's precisely the normalization which links the two in a nice way. So in a way, I think this normalization appeared already in Tian's Dink and Tian paper, actually, before Paramount. But anyway, that's the normalization that works. So for many points of view, it's a natural thing to do. There are also other normalizations which are quite efficient. It's not the only one that is really, but it's one of the natural ones. Okay. So where we are, yes. So we now want to see what we can do with the generalized Ritchie flow. So the generalized Ritchie flow, let's just recall briefly, has been studied, discussed a lot in this seminar. But you can think of it precisely as we did in the Keller case. You start with something which is essentially Riemannian metric. It's the so-called generalized Ritchie flow of Jeff and Mario, who wrote a book. But it's a flow essentially. It's a coupled system for a Riemannian metric and for a treeform, closed treeform. And they have to satisfy some coupled equations. So the first is essentially as the Ritchie flow, but you add this two zeros tensor, which is just the contraction of H, of two arguments of H, I guess, through the metric. And H itself just satisfies a Hit equation, a linear equation. So that was what this working group is about. And we saw that there is a general result. Essentially, it's a Stritz-Tian type of modification of it. Is that this has the basic local properties of the Ritchie flow. So the solution exists for short time. It's unique. And what's amazing in the story, which still amazes me, by the way, so many years after this appeared, is that miraculously, if you start with a generalized Keller structure, which I think of as biherbician, then you could supplement a solution with isotopies of complex structures, so that it stays a generalized Keller. And this is precisely the way this complex structure behave. I think Jeff gave us a very detailed exposition of this fact. So nothing is obvious in this story, at least to me. And the one way this was established, and what Jeff actually told us was to, so probably just return by this relations, I could use the isotopy of diffeomorphisms generated by these Lie forms to make J, say, fixed. In this talk, J will be fixed. Kind of a so I will act on the solution of the flow by this isotopy of diffeomorphisms determined already by the duals of the Lie forms. See these Lie forms. Just a composition of codifferential of the fundamental form with a corresponding structure. So we can always do that for the time when the flow exists, and we will end up with a flow which is defined on a fixed complex manifold. And we learned from Jeff's talks that what you get is a so-called pluriclosed flow. Magically, it turns out that the solution gives you a solution of a Hermitian matrix. This is Hermitian, and it satisfies DDC J omega T 0. So because of this, I will do this systematically. So I will work in the J fixed gauge because it resembles precisely what we encounter in the Keller case. So one thing that you should bear in mind is that all this discussion about topological abstractions that we started with still generalizes with some appropriate modifications. Now, the modification we need here is that we don't have Durand classes because omega T is not in general closed, but it's, as I said, it's this pluriclosed condition, it's DDC closed. And actually in complex geometry, they have been studied this cohomology, Apli cohomology, which is just the space of 1-1 differential forms, which are DDC closed, but you quotient by the image of D and DC instead of DDC, because if you quotient by DDC, that's infinite dimensional. That's not good. But this space is a finite dimensional. It's Hodge theory about that. So this group exists a finite dimensional, and moreover, what you could see immediately, it's a simple observation, is that there is a map from the second Durand cohomology to this H11 of these spaces, and this map is very natural. You take some representative of a Durand class, it's a two-form, closed two-form, and you take the 1-1 part of it. Now, if you play with the fact that the initial form was closed, you can see immediately that this projection to the 1-1 part will be Digi-bar closed. And now if I take another representative of the same Durand class, it will differ by differential of a form. And when I take the 1-1 part, you will get D of alpha 0-1 part. So the D of the 0-1 part of this one form plus D bar of the 1-0 part. So you end in the Apli cohomology automatically. So in particular, I can see that this guy is kappa of rho b, which also lives in the same finite dimensional cohomological class. So I can do the same, precisely the same game with as before to find cohomological abstractions to long time existence. And if you do that, you will end up with a similar situation. But the difference with the Keller case is that nothing is proved. So it's a conjecture. It's completely open conjecture. So that's the conjecture of Stritz and Tian, is that actually the solution will exist as far as this appli class satisfies the following. So the alpha t appli class given by alpha 0 minus 4pt kappa c1 will still contain a positive definite 1, 1, 4. By the way, right, so this appli cohomology is dual to the Bott-Chern cohomology in n-1 and n-1 degree. And this positive definiteness can be restated as positive definiteness in Bott-Chern, so by duality. So there is a dual statement as well, which is a little bit more closer probably to some topological consideration. But yeah, that's the situation. However, there are some results. There are very few results that have been obtained in a convenient generality. So one of these results, Jeff mentioned it, and it was a work that I have been involved too. We considered a special case when the starting bi-Hermitian generalized scalar geometry was non-degenerate. What this means is that the real the holomorphic Poisson tensor, if you prefer, is non-degenerate at each point, or if you prefer the real language, this means that you take the commutator of the two complex structures, inverted by the metric to obtain a 2 vector, and you want this 2 vector to be non-degenerate, non-degenerate at each point as a 2 vector. And this condition immediately implies that the first Chern class of either of the complex structure is 0. Furthermore, we show that this condition is preserved along the flow, and the flow exists for all time, which could be seen as kind of a confirmation of the conjecture or some sort of analog of Tsao result. But we didn't get to a complete convergence result on no generality. So convergence is still much more problematic in this generalized scalar situation. Okay, so what I want to do essentially, that's kind of after this introduction, the motivation is to see what we can do in the Fano case. Can we show long time existence? Can we attempt to prove some convergence to a Keller-Einstein metric? So we just want to see if the generalized scalar case could be treated with some sort of methods from Keller geometry that we already know. So that's the rough motivation. So why Fano? So what will be the relevance of Fano in the generalized scalar setting? So first of all, we can say immediately, well, Fano, it's already Keller. It's a Keller background. It's a bit probably limiting from the point of view of generalized scalar geometry, but nevertheless, the Fano condition is quite natural. That's what I want to tell you. So there are various specificities of the Fano condition. So for instance, we know that Fano manifolds are simply connected. We know that they don't have 2-0 forms. They are projective, therefore Keller. So in particular, by Bochner, H20MC, the 2-0 topology group is trivial. By Hodge duality, the same is true for 0-2. And in particular, the second Durham homology is the same thing as H11, real 1-1 forms which are represented by close. And because of that, you can see actually that this kappa, which goes to H2 to H1 aptly, is actually isomorphism. Well, that's not immediately clear, but you use Dirichlet lemma to show this. So this kappa is an isomorphism. So so essentially this whole discussion about appli classes can, again, in this Fano case, be reduced to the usual discussion in the Keller situation. So now what we did in the Keller case, we normalized the flow, and we will do the same thing here. So we will normalize it in some sort of a clear way. So instead of the original generalized Keller Ritchie, we will add a factor of 2 in here. The same local representation trick allows to go from the generalized Keller Ritchie flow to this normalized version, and in particular, this will be pluriclosed flow. We can see from immediately, and therefore you can look at the what's going on in the appli classes. We already saw, but the same thing will be true in the level of the RAM classes, because kappa is isomorphism. So in particular, in this particular case, there will be no abstraction for long time existence. So the main relevance for us, perhaps, in motivation is that the Fano case is a candidate where there is no any cohomological abstraction to long time existence. So we would expect long time existence from here if you believe in Street-Sentian conjecture. So that's one thing. So the other thing is that we will actually be interested in generalized Keller structures of symplectic type. So just to recall from Francis and Marco's talks, what was this? We saw I think three different definitions of generalized Keller structure of symplectic type. So I will probably give you another one. I'm afraid that this story will go on. It's different, but from my point of view, I want to think of generalized Keller structures of symplectic type as a bi-Hermitian data given by I, J, and H, Riemannian metric G, and I will impose the existence of a symplectic 2 form. So there is the existence of closed 2 form F, which with the following property: if you take the 1-1 part of this symplectic form with respect to J, with respect to I, you get the corresponding fundamental forms. This is one possible definition, and the point is that from this condition, if you have such a form, and if you fix, let's say, J, as I do, you can recover the structure completely. So first, by the first relation, actually, if you compose this 2 form by the complex structure and take this minus symmetric part, you recover the metric. If you consider the skew symmetric, this gives you kind of a 2-0-0-2 form with respect to J, but the differential of it will be precisely the torsion H, and you could recover the second complex structure by conjugation with F. Essentially, I and J will be conjugated to each other with respect to F. So that's equivalent to any other definition you have seen, including the one that you have a generalized Keller structure on T plus T star, where one of the structures is associated to F. We saw in Francis' talk a point of view where you fix the holomorphic Poisson structure, and so all these things are equivalent. So now, what is important from this perspective is that if I fix as I want the complex structure, then generalized Keller symplectic structures of symplectic type are entirely parameterized by the symplectic form, by one symplectic form. So what you do, you take a one symplectic form which satisfies the first condition. So we take symplectic form with this. So this, in symplectic geometry, people say that F times J. And then what you do, you could always do that because of the 1-1 part is positive definite, so it's non-degenerate. So this is automatically symplectic form, and you can always introduce. This will be a almost complex structure in general, but perhaps not non-integrable. So the generalized scalar situation is where the second complex structure is also integrable. So the integrability of I is here the key condition for this point of view, and it's non-linear. So integrability here is what makes this story complicated. So we will consider generalized scalar structures of symplectic type as just given by closed two forms which tame J, and such that this second integrability condition is satisfied. So this is all good and nice, but you probably immediately observe that there is no any reasonable structure in this space. So we are kind of when we do PD, you want at least to have Fréchet spaces. So from this definition, it's not clear even if you have continuous families of solutions. And happily, we review in this seminar this Hamiltonian flow construction, which provides actually nice continuous families, and I will just recall what it is. So we start with one generalized scalar of symplectic type. You can start even with a Keller structure if you want. And we know that it defines a Poisson tensor, as we saw before. And this Poisson tensor can be used to form diffeomorphisms. So you take a time-dependent function and you consider the time-dependent vector fields, which are just the differential of this time-dependent function, coupled with the Poisson tensor sigma 0. So this gives you a time-dependent vector field, and you consider the isotopy of diffeomorphisms this time-dependent vector field defines. And this is a result of Marco that in this case, actually you can use this to define actually a family of symplectic forms in our space for T small enough. How you do that? Essentially, you define you define first the corresponding complex structure. It will be integrable by definition, as we see, because I will act with this isotopy of diffeomorphisms to the initial one, which was already integrable. So the integrability condition is automatically satisfied. And observation is that this, if you define Ft by this expression, you satisfy the defining condition. So you stay in this space of generalized Keller of symplectic type. So this was very nice to review. Let me just mention that this also works in the Keller case. It's this construction of this flow construction actually is precisely what we saw in the first part of the talk. Actually, if we take the starting data to be just a Keller metric, then this Poisson tensor is trivial. Then this Hamiltonian, these diffeomorphisms that we constructed will be just trivial, and therefore, if you follow the formula, this IS will be just the initial J, nothing happens, and then because of this, so this will be IS will be still J. So I can write. So this construction will give me a perturbation of the initial Keller metric by adding a DDC a time-dependent function, which is just this integral of FSTS. So this flow construction precisely corresponds to this notion of Keller class that we saw in the Keller case. Okay, so that's important to observe. So we can think of this Hamiltonian flow constructions as a way to create orbits of within this space of generalized Keller of symplectic type, and we could think of these orbits as some sort of extension of the notion of relative Keller potential. And this point of view has been used by this paper with streets and myself I mentioned in the non-degenerate case. So now one observation, kind of a nice and key observation, is that if we start with the initial generalized scalar structure of symplectic type, as I defined it before, along the flow, along the generalized scalar Ricci flow or its normalization, will still remain in this category. So the generalized scalar Ricci flow gives you another way to see that this space of generalized scalar structure symplectic type is connected, so it contains paths, families of elements. So this has been established by a brute evolution formula calculation. So the idea is that we saw one of the three other definitions of symplectic type require that I plus j is non-degenerate as in the morphisms, and then the symplectic form was given by this. So what we did, we just took the flow and we computed the variation of along the t derivative of the players here, and ended up by this very nice evolution equation. So the idea is that if the flow exists until time capital T, you could define ft by this formula by just integration, and you will get a proof that it's of symplectic type. So this is important, and it will be used in the sequel. So, but before I continue, I probably want to make two general remarks. So far we had this Hamiltonian flow construction, which we want to think of some sort of a generalization of relative scalar potentials, and we have the generalized scalar Ricci flow. And
I have one question about the previous formula.
Yeah.
In the evolution of, yeah, so is it known a priori that the 1-1 part of ft with respect to j is omega t, or this is not?
Yes. This was our definition. You remember that how I introduced? Yeah. So yeah. So just here. So that's how we introduce them. So we just consider two forms which are symplectic, which tame a fixed j. So this, so the 1-1 part, will be by definition actually,
okay.
Yeah, because of this.
Okay, but still you get this information that in the Breuer closed flow, if you consider the evolution of the 2-0 form, then this is given by the evolution of the 2-0 part of f. I guess this is.
Yes. So the idea is to define ft by the formula that I showed you. Okay, so you know that the flow exists, and we use this proposition to define the 2002 part that you miss. Okay.
Thanks.
And at each finite time, this shows that it stays of symplectic type. Yeah, so I want just to make a brief comment about comparing these two things: the Hamiltonian flow, or this idea of generalized scalar class, perhaps. Who knows? Marco may think otherwise because they have a little bit more general construction, but I think that's very sensible object. And on the other hand, this flow. So the idea: can you expect this flow to preserve this Hamiltonian flow orbits? And in general, of course, not, because just because of proposition 1, the Durham classes of the derivative of ft will be a constant, minus 4p times c1 and j. This is because of the previous proposition. And if that's guy is non-zero, this ft dot will be non-zero. Whereas here you see that f dot FT is easier. So yeah, you kind of win and lose, but it did turn out that in the non-degenerate case, for instance, miraculously the generalized Ritchie flow flows through this Hamiltonian flow construction. That's also the case where C1, of course, is 0. So this abstraction doesn't. And you can ask similar things about the normalized generalized Ritchie flow, but then, of course, this is not clear, and this. I still feel that this should be somehow true. It depends how perhaps we precisely define these orbits. But let me just say some kind of a probably nonsensical remark. But even if we were able, imagine in the best of cases that if we start with the generalized Ritchie flow and we can interpret it as a flow of functions depending on time derivative. And such that when we do the Hamiltonian flow construction, we get precisely the orbit of the flow. That's not clear that this will lead to nice PD theory, because what you have to do, this is it's a function that's good, so it's kind of a scalar thing, but then you have to integrate this. You have to take the differential, you have to take this time-dependent vector field, and then you have to consider isotopy of diffeomorphisms, and you have to act on the initial object and then solve some PD. And taking this diffeomorphism is something that I don't think has clear sense of a differential operator or something. So it's not clear to me, even if it were possible. Of course, this will probably be used in terms of some maximal principles, but it doesn't give you a direct reduction of the PD. So it's just. Now, that just I'm expressing, so yeah, so this is a remark to tell you that there is another idea that we will probably promote, I will promote more in the next lecture, but there is another way to think of this scalar reduction. It's completely different from what we saw already. I will stick for the final case, but that's more general. So it works for the symplectic type modification of the flow. So we saw by the previous proposition is that if we start from symplectic type, it stays symplectic type, and I have this nice relation for the corresponding symplectic forms. What happens is that well, in the final case, we know already that this FT will stay in 2PC1 MJ. In more general cases, you have to use Demaipon to see that this FT will define a Keller class if you are already in a Keller manifold. If the background manifold was Keller, in general, the fact that FT, the 1-1 part is positive definite, this means that the Durand class will be Keller by the Demaipon result. So what happens is that the Durand class of FT will be a Keller class. In the final case, it will be just the fixed C1, which is positive definite. But then by Yao theorem, we can find a unique Keller metric in that class, omega bar T, which has a volume given by the volume of FT. Okay, so you solve a Monge-Ampère equation to do that. And now what will happen is that we can play the same trick as we did in the Keller case. So so you have rich time, you have this omega bar, which is a G Keller metric which solves a Monge-Ampère, and it will differ from the original one, which I associated time 0 by a function. So you given this generalized Ritchie flow, you have this kind of a trade, this imprint in the Keller world by solving this Monge-Ampère. And I guess the new idea that's allowed us to make some progress, it was that well, so let me probably project everything. So of course this new idea would work if you could really say something about this solution. So in general, it's completely implicit. But if you could link or kind of recover the initial flow from this Kähler reduction, then you probably could say something. And that's I guess our main point is that we will observe, and I will discuss this in detail next time, that this can be done in the toric case. In the toric case, it turns out after some tour de force we did, is that finally this strategy would work. So I could explicitly find this object, and then reduced to the initial generalized Kähler-Ritchie flow, which is rather complicated, can be reduced to geometric flow on relative Kähler potentials, and which we can attack with more conventional methods of Kähler geometry. I could. So how much time I would have? I probably have to stop here. Or if you allow me 2-3 more minutes, I will probably tell some.
Sure, that's fine. Yeah, that works.
Okay.
Yeah.
So next time I will discuss the toric assumption, but I just want to give you a bit of a motivation.
Could I just ask about the last thing you said?
Yeah.
Could you go back? Yeah. So sorry, do I understand it right that what you're describing is you're saying choose a so if you have this f sub t, it gives you a volume form, and then use Yau's theorem to get a actual Kähler, a unique Kähler metric, which represents that volume form. And then you describe the generalized Kähler-Ritchie flow in terms of that auxiliary Kähler metric.
Yes.
And write the PDE in terms of Kähler potentials, just
Exactly.
pure reducing everything to the Kähler.
That will be the that will be the.
It's almost like the generalized Kähler dynamics has a shadow onto the Kähler dynamics, and you do
Exactly.
it in the case.
Yeah, precisely. The whole point is that in the toric situation is one of the rare circumstances that you could do this explicitly. So to go back and forth from the Kähler picture to the generalized scale. So in general, this has the default of being very abstract. So even though that there are in Kähler geometry some results about this Monge-Ampère map, but it's still very kind of. But in the toric situation, this could be done explicitly. Yes, exactly. That's the idea.
But somehow is the point that when you project it into the Kähler world, it becomes easier to analyze, or like that you have pre-existing results and somehow it's not manifest on the original problem, or what is it?
No, actually what will be important is that we'll reduce to a scalar PDE to which we can make the estimates needed. Actually, with it's a different PDE that has been studied in Kähler geometry. There is no Kähler geometry result that covers this specific PDE we get on the Kähler side. But as I explained, what, for instance, this Tsao result would work. It doesn't work directly, but it will. So we will get a C0 finite time C0 estimates for this relative Kähler potential, and we will use them precisely as Tsao will use them, but we use instead of Yau estimates this Jeff's work that with Krylov, which allows us to return to the generalized Kähler-Ritchie flow and to say long time existence. It's kind of a more complicated, but I don't think this problem was studied in Kähler geometry, but as you see, it's a very, very interesting problem. It's a kind of generalizes very naturally to problems that have been studied in Kähler geometry.
I see.
So it may be that there are some pre-existing literature that we are not aware of, but yeah, it will be reduced to, in the toric case, to a real Monge-Ampère type.
I see. Okay.
I mean, also, I think on like a more basic level, somehow in the toric setting, you do end up achieving like a complete description of the time t data just in terms of one potential function somehow. Yeah. I mean, that's really the analytic advantage.
Yeah.
That, well, I guess in the toric case, you get it sort of either way. I mean, I guess Vesti described two ways. Like you can get it from the flow construction. You can also get it from this, from the, you know, this trick using Yau's theorem, as you mentioned.
So maybe I kind of, yeah, I'm hesitant here, but probably just allow me a couple of minutes to tell a few things about why this toric thing is interesting. Yeah, so what is toric assumption, first of all? So it's a very simple assumption. You take the automorphism of your Fano manifold. It's a finite-dimensional complex group, and you want the max. So it has a maximal torus. All maximal tori are conjugated to each other. You take one of these maximal tori, and you measure the dimension of this object. And you want to be half of the real dimension of the manifold, equal to the complex dimension. And it's the highest allowed by some general observation. You cannot have torus bigger than this dimension. Many ways to see this, but anyway, so this is essentially a maximal rank. So these are Fano manifolds to which the automorphism group has maximal rank possible. There are many examples. But the main point of the toric geometry is that there is a very nice way to describe and classify this object, and these objects are classified by the Zahn polytope. So there is this very beautiful theory. I will review it briefly, but if you take CP2, for instance, it will be classified by a polytope in R2, and it will be just a symmetric triangle or simplex, standard simplex. Or if you take CP1, for instance, this will be another example of toric Fano, and then you will get just a square. And so far, and there is a combinatorial way to characterize them, and in particular, you could create examples. For instance, you could cut corners in symmetric ways, and so forth, So essentially, this is a class of manifolds which is big enough and specific enough to work on and to probably make conjectures. That it has been pretty much studied in algebraic geometry from that perspective, but also in global analysis. And in a way, what we are doing is just took this assumption to see what happens, and we revealed some interesting things which we believe probably are kind of which predicts much deeper links to the general case, which we still don't understand well enough. Yeah, so next time I will have to review a little bit the historic geometry going from the Zahn, Gilman, Abreu. There are two very interesting works in generalized scalar geometry by Boulanger, which has been also generalized more recently by Wang. So they essentially classify this generalized scalar structures of symplectic type on toric manifolds by very simple data, by one function and two constant bivectors in the Lie algebra. And because of this simplification, the description of the structures will be very, very simple, and we could rewrite the generalized scalar Ritchie form in a very specific way, and we can take advantage of this idea that I just discussed. So I probably stop here and continue next time. Yeah, thank you.
Yeah, thanks, Vesti. Are there any more questions?
Thanks for explaining it so carefully, and also thank you for doing the Delzant stuff next week. I'm going to tell some students who are not in generalized geometry to come anyway, because I think they would benefit from hearing you talk about toric.
Yeah, thanks. So yeah, I would try to make some introduction that would put things in perspective, but yeah, time is always limited. Okay, thank you.
Okay, yeah. Thanks, everyone.